Hello, everyone. So welcome to the RSMA webinar series 2025, organized by Communication Society, WTC Special Interest Group on RSMA. So my name is Won Shin, and I'm an associate professor at Korean University, South Korea. So this is our second webinar series this year, and it's our great honor to have Professor Kai-Kit Wong from University of College London, UK, as our distinguished speaker. So please allow me to make a brief introduction to Professor Kai-Kit Wong. So he was born in Hong Kong, and I received a bachelor and master and PhD degree at all from the Hong Kong University of Science Technology. And he is a chair professor of wireless communication at Department of Electric and Electronical Engineering, University College London. And after taking appointment at University of Hong Kong and University Hall of the visiting position at Lucent Technology, Bell Lab, and Stanford University, US. So his current research center around 6G and beyond mobile communications. He is one of earlier researcher who proposed a multi-user MIMO, and like his first paper on multi-user MIMO was published in WCNC 2000. It's very early, right? So yeah, which appears to the first ever research paper on this topic. Yeah, he is a fellow of IEEE and IET, and he served as an editor-in-chief for IEEE Wireless Communication Letter between 2020 and 2023. All right, so before the talk, I'd like to remind the rules of our webinar series. So during the 50 minutes talk, please keep muted and you can just type your question in the chat box during the talk. But after the talk, we have a 10 minutes Q&A session, so you can unmute it and raise your questions. So otherwise, I can pick up a couple of questions in the chat box. All right, so enjoy the talk. Let me stop the sharing. And the floor is yours. Kit.
Okay, so thank you very much. Okay, let me start my slides somewhere, and then I'll share. Okay, so tell me whether you actually see my slides.
Yeah,
right?
I
So
can.
that
Yeah,
okay.
perfect.
So everything is all right. Okay, so of course, I have to okay, just make sure that I have the control. Okay, cool. So first of all, thank you for Bruno for inviting me. Okay, give me this opportunity to share some of my research work. Okay, in this webinar. Okay, for RSMA, and thank you for Professor Wen Jae for introducing me, and Steve as well, doing a lot of logistics and everything is that make these presentation or seminar series possible. So if you look at my slides now, okay, the title is Can Free Antenna System Make RSMA Better? So this is a webinar, okay, for RSMA. So the focus will be RSMA, okay, that will be nothing else, okay. But of course, okay, speaking on RSMA, I can only say that I'm not expert in RSMA, okay, everybody knows, okay, you guys are expert. So I expected a lot of audience today listening to my talk actually are more knowledgeable in RSMA than me, okay. So, but what I like to do is actually try to provide you another perspective, from someone who develop interest, in RSMA, but not as an expert like you guys, but try to bring something slightly different, or probably from my side of expertise, working on a free antenna system over the past few years, and see how my research actually intersect, okay, with RSMA, and hopefully this is actually a meaningful marriage, okay. So in the end, and then you can judge on whether, okay, this is the valid point, or is it like an interesting application that could combine these two technologies together that make RSMA better, okay. So I also like to thank, okay, my postdoc, Fasha, okay, Fasha. Actually most of the work that I presented today is led, okay, or done by Fasha, okay. So let's get to it. Okay, so I think everybody, okay, including myself, of course, our research is motivated by 6G. we're in the midway of the development of 6G. There has been a lot of discussions about what technology should go into 6G. There are a lot of names, okay, floating, okay, in the community, right? Master MIMO or extra large MIMO, okay, RISC technology, AI, and RSMA as well. And I actually like to congratulate the team, of Bruno and his collaborators making these so successful a story about RSMA. And then, I certainly keep an eye on the recent developments. Okay, on LinkedIn, I see a lot of great news actually happen over the past few months. Okay, RSMA being considered in 3GPP, etc., etc. So this is really everything looking really, really good. But if we look at 6G, what do we want actually 6G? So 6G mean many things, so many different things. If you look at these sort of a couple of hexagon, shape thing, okay, you will see a number of key performance indicators that everybody knows that, we will need to achieve, okay, all of this, okay, maybe not at the same time, but okay, combination of these would make some interesting use cases. So sometimes it's pretty confusing, okay, as researchers, because there are so many targets that we need to hit, but sometimes we don't know how to translate those targets into something that we're familiar with, okay, in order to drive our research. So therefore, I particularly like to bring to your attention about a paper that published 2 years ago from a team led by Professor Yao Xiaohu from Southeast University in China. So this paper is a very clean paper, I would say, because they provide an interesting interpretation of what 6G would want, okay? And in particular, they give it a very succinct, okay, concise message about what 6G is about. In their own words, okay, so 6G means PK mean extreme connectivity. It's about driving to extreme connectivity. So what does it mean by extreme connectivity? It includes three crucial elements. The first is T. T is terabit per second scale data rates. Okay, we need to drive up data rates. Okay, so second will be kilobit per second per hertz spectral efficiency. So we need to drive the spectral efficiency to be very, very high. Well, of course, if you have strong background expertise communications, that data rates and spectral efficiency are two different things. But some people, if you are working in cross-field or whatever, you may feel that, okay, are they the same? Okay, actually, they are not the same. Data rates, as long as I give you sufficient bandwidth, you probably will be able to hit whatever number you're going to hit. But it doesn't mean that it's easy, because operating in certain bands, okay, you will face challenge about implementation. Like, okay, what is the cost of operating device at, let's say, millimeter wave band or terahertz band, or is it energy efficient and things like that. So therefore, technically, it's still very, very challenging. But communication theorists like me, okay, I wouldn't, worry too much about terabit per second data rates. So what I need is bandwidth. But I cannot say the same thing if I focus on spectral efficiency, because the spectral efficiency is all about, I give you the spectrum, okay, let's say 1 hertz, now how many data rates, okay, how high the bit rates that you can retrieve. For example, in these, it states kilobit per second per hertz spectral efficiency. That means if I give you 1 hertz of bandwidth, you need to hit 1,000 bit per second. That is, a hell of, data rates that you need to push through in a very, very tiny portion of spectrum. So to look at it, how this is achievable. So basically, I think that means that we need to allow the spectrum sharing to be done very, very aggressively. So therefore, that would be strong interest that we should be allowing multiple users to be sharing the same spectrum. This is where NOMA, RSMA became so popular over the past few years. I think it's all about driving up spectral efficiency, okay? So the other point that I think these extreme connectivity, which is cool, is about the mu here, okay, the mu here. What is the mu here for? Mu meaning microsecond scale latency, okay? We need to reduce the latency as well. So we heard about this URLLC, right? In the 5G development. Now in 6G, similar, okay, but people talk about hyper, right? HRLLC, something like that, okay? So hyper reliable and low latency communication. It's kind of like the same thing, but the message is the same. We need to reduce the latency. So according to latency, of course, this talk is not going to, we won't be focusing on latency that much. but actually it's kind of related, because when we talk about latency, so what comes into mind? Complexity, okay? So complexity of the protocol, decoding latency. So, oh, that means what? That means that maybe, all these dramatic, okay, powerful error correction code, maybe, we can use it, but we may not be too crazy about this, because, a bigger code work, okay, longer code length is going to cause you longer latency in terms of delay. So this is not something that, we would encourage if possible. So these are actually related to the discussion, when I try to analyze what RSMA can offer to us. So now, okay, RSMA, okay, rate splitting multiple access. Everybody know what is this, okay? So this is a quick summary of how I see RSMA, okay? So I believe RSMA is very specialized for its unique way of handling interference, because it makes, kind of like two regimes together, okay? One is the noise limited regime, and the other one is the interference limited regime, okay? So in one extreme, when we treat noise, we treat interference as noise, of course, people know, how we're going to deal with it, or maybe, some kind of a no mass to, a strategy, okay, doing interference cancellation, something like that. Or if we treat, interference to be like a very extreme. So maybe one way of doing it, for example, for RSMA to do it is using the concept of rate splitting, right? So when you encode the data, you already encode it into, like, partition it into two parts. One is the so-called common part, the other one is the private part. So this is nothing to do with information confidentiality. So some people would be mistook it, but in the end, it's about how do you structure the data into code work, okay? Share the code work or individual code work. That would, benefit how do you manage interference. So this is kind of like a very, very niche and then a smart way of handling this, okay? So of course I like NOMA, okay, but of course, if I need to compare NOMA and RSMA, okay, I don't want to put myself into a very difficult position and say, okay, which one is better. But I do see that RSMA kind of provide a more general framework that actually kind of include what NOMA does, okay? But then on the downside is that because RSMA is so general, it kind of look it into a very, very general version of NOMA and beyond. Then we will need to entertain this multi-layer rate splitting operation. This actually is crazily difficult, right? It's so complicated. So therefore, in fact, if you ask me what I like about RSMA, I actually particularly like one layer rate splitting operation, okay? So the more layer thing, okay, people can do it, okay, can make fun of it, but I probably would have a little bit of reservation because of all these complexity go with it, okay? But one layer rate splitting actually is cool, okay? Because by doing this one layer rate splitting, it's kind of said that, okay, you don't need to use the grouping ordering thing like NOMA normally required to do, because for NOMA to work well, you need to do this sort of, let's say, power domain NOMA, you need to make sure that the order or select the users which have certain channel characteristics so that the interference cancellation would be done effectively. Otherwise, you're doomed, or, you can still do it, but, it wouldn't be able to deliver the spectral efficiency advantage that NOMA normally expect. So therefore, kind of RSMA, kind of, even though people normally would take it as a more complex approach, but actually, if you look at the details, it could be actually simpler, okay, in some sense, particularly from the transmitter scheduler point of view. So I kind of like this. So, but of course, because remember the objectives that I raised above 60 is about massive connectivity, massive access. Why? Because we need to share the spectrum to as many users as possible. This is what hopefully RSMA may be able to do it for us. Okay. So therefore, I kind of try to analyze RSMA from this light, even though I know RSMA can be addressing other challenges, not necessarily market access. Okay, it could be user fairness, it could be all this, all this stuff. Okay, QoS, whatever. Okay, whatever. Okay, so there are a whole lot of bigger world which I'm not familiar about in terms of potential for RSMA. But to me, my main interest will be massive access. Okay, let's try to see if we can use RSMA for massive access, and if we do, what issues that we may catch our attention that we may need to address more carefully. So this is a basic to use the RSMA system, which I actually took from the I think from the special interest group, okay, of these RMA guys, okay. So therefore I didn't create this picture, but I actually like it because this picture show very, very clearly, the operation of a, let's say, 2-user RSMA system. For more user is the same, okay. You just add, more users in the diagram. It doesn't change anything. So basically, if you're a multi-user, you just schedule the user, okay. Remember, you have different messages, okay, W1, W2, or maybe WK, whatever. Then you split the message into the common part and then the private part. This is the subscript C and then subscript P here. So once you get the common message across different users, so normally you will combine all these common message across users together, okay? Because these actually create a better architecture when you do decoding, okay? You don't want to decode individual, a common message and then do interference cancellation. So this would be crazy. So therefore, this is kind of like a normal way to do it. And then after having the common message, private message, and then of course, you raise it to the signal space, and then you do precoding if you have multiple antennas, okay? So therefore, this is also, RSMA is also quite ready, okay, to be integrated with existing MIMO system. So therefore, you can do existing MIMO system, but then you put it like a RSMA layer onto it, and then just to see how do you handle data, and then change the decoding architecture to have a little bit of uplift about the interference rejection capability. So at the receiver side, all the users do this more or less except the same thing, but focusing on their own data. So user one would be like, okay, let's decode the common message first, and then using the splitter to take back the common message belong to this user. Okay, so that's how they get this back. So, and then with this, okay, they need to re-encode this common message so that they create or activate the interference, and then they would cancel it, okay, with the channel knowledge. So after they cancel the interference, then they would try to decode the private message, okay? Then, after you decoding, and then you combine, and then you get back your own message. Okay, now, everything looks all right, okay, theoretically, everything looks fine, okay? So other users would do the same thing, but we cannot forget, right there, if you try to decode, of course, the first thing you do is to decode the common message. And then when you decode the common message, you know that you're going to have inference of the interference from the private message. But of course, these somehow should be dealt with, hopefully, satisfactorily, because of the design of the coding, okay? Because when you code, the data, partition that into private and then common, so I think kind of like the Hamming distance or whatever, okay, you need to try to separate this all apart as possible, so that, okay, it would improve, okay, the reliability of decoding the common message when you suffer from interference caused by the private message. So these should be dealt with, but at the same time, we cannot consider it as so the ideal. There's going to be private messages becoming interference that, would affect the reliability of decoding the common message. But how about the decoding of the private message? So of course, the underlying assumption is that the common message needs to be decoded correctly. If it's not, then your estimate of interference would be off. And then when you try to subtract it, you create more interference, okay? So therefore, there's a problem right there. So we must, okay, ensure the common message needs to be decoded correctly. But then even the common message is decoded correctly. So then you subtract it, that's fine. But then still here, when you try to decode the private message from user one, there would be interference about the private message for user two, user three, user four, user five, depending on how many users that you allow them to transmit at the same time, same frequency. So therefore, it is clear that, okay, things could work, okay, but only when interference cancellation or decoding is done properly. Otherwise, things go like haywire, okay, and then we will need to deal with the rest, okay. So that could be a disaster if decoding is not done properly, okay. So therefore, of course, one legitimate issue that I actually, this one I actually copied this question and answer from the special interest group website, okay. So I didn't create this, okay. I actually got it from the Q&A, okay, one of this Q&A in the website. And then, okay, so this actually caught my attention when I prepared this presentation. Is there any situation where the common message is decoded successfully? So these even assume that, let's say it's fine, the codebook is large enough, okay, and then we could have sufficient separation between the common message and then private messages. so that when we decode it with the presence of the private message, it's okay. The common message could be decoded successfully, but still the private message is failed to be decoded at the user. Is it possible, right? Now, this is the answer, okay, prepared from the, I think, the management committee, okay, of the RSMA special interest group, okay. So therefore, it should be very fair, right? Okay, because you guys make the argument, not me. So it say, okay, most of the literature works make use of Shannon, okay, theoretical concept, okay. So under Gaussian signaling and infinite block length, okay, remember that, okay. So the ergodic rates are achievable and no SIC, okay, successful interference cancellation error occurs. Okay, so this is actually the assumption, the baseline here, which is kind of cool. Okay, when we look into theoretical analysis, this is all the time. I did the same thing. Okay, in theoretical work, but in practice, if finite block length is considered, error would occur, and SIC, successful interference cancellation, would be imperfect. Okay, so under imperfect SIC, it is possible that the common message decoded successfully, but the private message would still be decoded unsuccessfully. Okay, so of course, Bruno and his team and other people probably have done a lot to address this situation and see, okay, what if, okay, so there are these decoding errors, okay, being considered, okay, and then provide some link level simulations there. So I would, okay, refer interested people to go into reading Bruno's paper and other similar work, and just try to understand what is the issue there, and then whether this is a serious issue or not. But I think in the end, okay, it comes down to the same thing, okay? It comes down to your signal to noise ratio, okay? So if your signal to noise ratio is high, okay, maybe this is less susceptible to that. But not only that, remember one thing. When we talk about private message, common message, on all that stuff, these interference is not noise. So therefore, noise level cannot be too high, but at the same time, even noise level is not too high, maybe that still cause you issue. So because you're sending your private message with probably a similar power level, okay, because you don't want to suppress your private message too much, okay. So there's of course some degree of freedom there. You can optimize the power control, like how much power to be going to the common message, how much power to go to the private message, and then there are some balance that you can do and trade-off you can do, which makes it a very interesting research problem as well. But okay, putting that aside, okay, let's say you have some reasonable power allocation there, but still, it doesn't guarantee that it will work perfectly, because in the end, okay, if you want to ensure, let's say, guarantee RSMA will be delivering the benefit, what would you have done? Let's say if you're engineers in some of this company try to make RSMA work. So if I were, those engineers, I would think, okay, I need to make sure this works. So therefore, the first thing I would need to do is I will make sure the error correction coding would be powerful enough, okay, so that the interference cancellation would be all right, okay, because this is the bottleneck, okay. If I cannot get the SIC to work correctly, there's no more RSMA, no more NOMA, okay. It's just blue sky stuff, okay. So therefore, what I need to do is I need to make sure I would have a strong error correction code. Let's say to protect the common message first. Second, I also may need to protect the private message as well, okay, because the private message needs to be decoded with the private message to other users. So how do you do it? Okay, if you do strong error correcting codes, you need to add redundancy. Okay, that's the problem. Okay, why is the problem? Because it's pretty ironic. Okay, RSMA is all about spectral efficiency. Okay, if RSMA say, okay, yeah, it's a more powerful stuff, but we don't deliver spectral efficiency of others, people will say, then why we go into that level of difficulty doing all that stuff, but not delivering the benefit in terms of the rates? So it doesn't make sense. But the problem is that if you add strong error correcting codes, that means in practice you add redundancy, more redundancy. Maybe what that means is like, okay, we do turtle codes, convolutional code, whatever code, okay, outer code, inner code. So rate 1/3 code, for example. Then if we talk about rate 1/3 code, what does that mean? It means that, in fact, you think you're delivering the benefit of one, let's say 1 unit, okay, capacity. No, you only get 0.33. That's what hurts you, okay, if you protect by applying strong error correction codes. So this is one problem. The other problem is, okay, maybe we just we don't add a lot of redundancy, but we use a longer code block length, okay? Longer block length, we would be able to play around with the structure of the block so that, you know, it will be all right, okay? So therefore, the block length is the main thing. Sometimes it's not just the redundancy, it's the block length. But the block length is another thing. Block length is related to decoding delay. So bigger block, okay. So then you need to, at the receiver, you need to wait for the whole block to be decoded, okay. You don't just decode part of the block. So that means, okay, longer block, larger block, then you have longer delay. And remember, we're talking about longer block length for the common message, for the private message. So therefore, there will be like at least doubling, okay, at least doubling the delay, right? Because you need to wait for the whole block for the common message, then you decode the whole private block, which is another big block. So therefore, when it comes to the real practical challenges of RSMA, that same goes to NOMA as well. If we need to make sure thick, okay, successful interference cancellation to work correctly, strong coding, long block length probably would be the ingredients, okay, that you need to play with. But once you apply this, maybe most of the benefits disappear. Then people will start look at RSMA or NOMA again and say, okay, maybe we shouldn't do it. Okay, that's too complicated. So therefore, we are at a crossroad here, okay, where we know why we want RSMA, but at the same time, there's issue to make sure that we deliver the full benefit and full potential of RSMA. And we, at the same time, do not want to use strong channel coding, okay? So this is kind of like a contradictory stuff, right? We want to deliver RSMA benefit, but at the same time, we don't want to protect SIC, okay? Because we don't want to do strong coding, okay? Right. Now, this is where maybe I come in, okay? So because my understanding is, okay, so the bottleneck is SIC. We need to make sure that is reliably done. But what if, okay, what if SIC can be done reliably with short block length, okay? No error correction codes, okay. Again, I believe in practice you will do this, okay? You will use error correction code. It's not like I argue that I don't use it, okay? But what I'm saying is that if error correction codes is an issue because of the redundancy, what if I go to the other extreme where I don't do any of this, okay? But then I still make sure SIC done reliably. If I can do this, that means we are one step closer to practical RSMA, right? I think that's the argument that I'm making, okay? I want to have practical RSMA without strong error correction code. This is the key. So how do we do this? Well, my proposal would be maybe we use spatial diversity, okay? But the one where the complexity probably would be more will be less, okay? So it's about for entire system now. So let's bear with me a few minutes so that I can introduce to you what is for entire system. But I reckon that maybe some of the audience today already know the story behind for entire system, so I'll try to make it as quick as possible. So for entire system is inspired by an idea, okay, from Bruce Lee. Bruce Lee, who is Bruce Lee? Okay, who's Bruce Lee is not a 5G or 6G engineers or scientist. He's a movie star and he's a martial artist. But of course, you know, I should say he was because he died in 1971, many years ago. And then a lot of people, of course, see him as a hero because he played a lot of movies at that time as well. But he's a martial artist. He's obsessed with martial arts. Okay, he know Wing Chun, karate, taekwondo, judo, aikido, Brazilian jiu-jitsu, boxing, you name it. Okay, all that sort of stuff that he know. Why? Because he's just obsessed with fighting. You know, he wants to like perfect. Okay, his skills about fighting or combat. Okay, so he learned so many different styles because he wanted to know the pros and cons of different styles. In the end, okay, he came up with his own style called Jeet Kune Do. Okay, this Jeet Kune Do thing, okay, is a new martial art system that he created. And remember, I said he's also a movie star, so therefore he actually used one of the TV series that he participated called Long Street, which was aired in September 1971. So he used one of the episodes to share his idea of Jeet Kune Do, okay, to the to the people who watch the show. So this is what he had to say, that I try to repeat it to you so that you're kind of having an understanding of what is his philosophy in combat. But then later on, I will try to make a connection with his concept to martial art to wireless communications technologies later on. Okay, so this is what he had to say. He said, empty your mind, be formless, shapeless like water. If you put water into a cup, it becomes the cup. You put water into a bottle, it becomes the bottle. You put it in a teapot, it becomes the teapot. Now, water can flow or it can crash. Be water, my friend. So this is how he approached fighting, okay, or combat. So the first part of his message, okay, clearly repetitive, okay, talk about bottle, talk about teapot, talk about everything, okay. But I think the main message of his philosophy is well summarized by his last sentence. He said, be water, my friend. This is his approach to combat. But how is that related to wireless communications, right? So then I need to try to make the connection. So first of all, what's wireless communication? In my opinion, wireless communication is the most convenient form of communication because we can send data, we can communicate from one point to another point without wire, without nothing, okay, in between. It's most convenient, but at the same time, is the most terrible thing that we try to do. It's most challenging because wireless communication channel is very unstable. So we always face difficulty about propagation distance because longer distance, less power get to the destination. So we could also have objects sitting in between blocking the signal. So we could also have what we call multipath fading because radio wave propagate into different direction, interact with the environment differently. So in the end, so when the multipath signal reassemble at the receive antenna, they could cancel each other. That make the signal disappear for a number of reasons. Okay, so spectrum is also limited and expensive. So therefore, we have strong need of sharing the same spectrums to a larger number of connectivity. So in the end, so we have interference. We have a lot of stuff that actually cause huge issues about wireless communications. So what engineers like us or researchers like us, what have we done, okay, over the past few decades? So we came up with many innovations, different new technology, for example, error correction coding, try to average out the noise, okay, we do power control, compensate the path loss. We also do adaptive signal processing because maybe the signal for one antenna is weak, and then we can try to assemble, okay, so mix, okay, signal intelligently across multiple antennas so that we establish a more stable signal for decoding. We have a lot of things that we can actually do, and then we do interference management and RSMA, NOMA, K-mean, interference alignment. The list is long, network coding. Really, there are so many new technologies actually keep on happening over the past few decades. What we have done so far is just one word to me to summarize. It's about adaptation. This is all we have been trying to do. And then these actually the ideas Bruce Lee actually perceived when he approached fighting or combat. Be water, my friend, is all about adaptation. It speaks volume, okay, about adaptation. So therefore, how do I actually utilize or being inspired by this concept? When Bruce Lee say, be water, my friend, maybe I'll just say, be water, my antenna. That actually leads to this new concept that I created back in 2020, but actually I had this idea more than 10 years ago, but we stopped publishing in 2020. So we used the name Fluid Antenna System to summarize, okay, the flexible nature of the antenna. So it has nothing to do with using fluidic material for antenna, even though this could be one of the options. But I don't really care how do we make it. And of course, I will show you very quickly some examples of the prototypes that I was involved to building as well. So what is Fluid Antenna System? Is this shape flexible, position flexible antenna system. This is what I mean by free antenna system. With this, okay, we could have rich diversity that we never have before. And this could potentially be the game changer for RSMA because then if you have sufficient diversity coming, not from error correction codes, but then you can still meet, successful interference cancellation work well. Why not, right? Then you don't have to pay the price about error correction coding, okay? So, okay, like I said, okay, full antenna system is real. I will go very quickly. Some of the prototypes is already there. So if you're kind of like not so sure what is free antenna system, that seems to be like a concept SIG flexible position factor antenna system. Okay, all right, but fine. But what does it look like in practice? Okay, it could look like many different things. It could look like something like this when using pump to shift the liquid metal as the antenna or the radiator inside container. Okay, but these design is good, but this design probably is not fast enough. Okay, for wireless communications. Okay, so there are other options like using pixel reconfigurable antenna, something like this. So basically, this is like a meta service structure. So all these entire antennas is made up of all these Legos. Okay, these Legos, the connection between the Lego need to be optimized somehow so that it create a new antenna every time a new combination is activated. So these would become a highly flexible antenna system that you can use. Okay, for wireless communication. So there's other possibility. Maybe we're using metamaterials. You have one piece of antenna, but these whole antenna surface is composed of metamaterial structures, which you can activate, deactivate a portion of the antenna aperture so that you can actually shift the radial aperture position so you can achieve position flexible antenna without mechanically moving any object. So this is very, very fast. It works based on pin down, so it actually switch in nanoseconds. So therefore, wireless communication, no problem, because wireless communication, the concern is about millisecond, okay, channel coherence time. So if we can hit nanosecond, come on, okay, this is too fast, okay. So actually, so therefore, I'm not going to go down all these prototypes too much. But if you're interested, okay, you can do contact me privately by email, whatever. I can have you explain. And of course, you can pick up those publications that I list there as well. So before I move on to how we integrate RSMA with free antenna system, I also like to bring to your attention some recent experimental works done by CDN University, Professor Wong. Okay, he actually picked up the reconfigured pixel free antenna system and then put it like an FPGA experiment and then try to do in real life. Okay, does it actually bring us any gain? Okay, so it turns out that this is a good result because this is about bit error rate. This is uncoded system. So therefore, uncoded system, by using these antenna, you can actually reduce the error probability by an order of magnitude. Okay, if you have, of course, sufficient signal to noise ratio. This is good news, right? And the reason why I'm showing you this is if experiment for uncoded system, for system would be able to deliver an order of magnitude reduction of bit error rates. That means in practice, you and a little bit of error coding, not too much, then you could easily bring, let's say, 10 to the power minus 3 to 10 to the power minus 6 or even minus 7. So then interference cancellation would be done okay, right? So you just need something to help you. And this could be something to help you, okay, for RSMA, okay? So there are a lot of, potential application that we can make use of for antenna system, but we're not going to talk about this today. So today the focus will be RSMA, okay? So, but before I show you 3 examples that we try to combine RSMA with free antenna system, relevant to this, it is important that I like to say that, okay? So how do we know free antenna system provide you a lot of diversity, right? How do we know, okay? So, and in fact, in order to understand the diversity gain of free antenna system, I like to bring to your attention these paper that we published last year in the wireless. Okay, these paper is actually try to target this problem. Look at a standard MIMO system, but we just let the MIMO antenna to change the position at the same time. Okay, so we have this additional degree of freedom and try to understand these additional degree of freedom, how much diversity that we can bring to the channel. Okay. So therefore, okay, so this table summarizes this. Okay, of course, the diversity at the end of the day is dictated by the size, okay, of the antenna. So this is the fixed MIMO, okay, the normal MIMO, okay. The normal MIMO, let's say this given size, okay, you get 16 is the diverse order, which is quite large. But if you allow the antenna position to change at the same time, you get 169. 10 times more diversity, guys, okay. So larger antenna, okay, 81 to 529 still extraordinary jump in the diverse order. That, okay, is the theoretical work that actually explain, okay, or illustrate the phenomenal diversity available in a finite space, okay, for free antenna system. So I think there's a lot of application that you can try to utilize fully this diversity order. So my understanding is that this diversity order, we can use it to help NOMA, to help RSMA, to make sure that they don't suffer from the spectral efficiency loss due to heavy error correction coding or due to large block length, okay? Then we can fix these successive interference cancellation, improve the availability, but without relying on, okay, huge, okay, error correction code, okay? So this is cool. So now, okay, let me just quickly go through my 3 examples, okay? But we certainly have sufficient time to go through this, okay? I promise, because I'm not going to show you equation and all that stuff, okay? I'm just going to show you what we did, okay? And then what, very quickly, what contribution that we made, and then what more can be done, okay? So the first work that we did is just simply combine free intense system and RSMA together, okay? So we have a paper uploaded last year, okay, in archive, okay? So for details about all this mathematical modeling, so, and all these in performance analysis that we do, okay, so please refer to this. But very simply, this is the model we consider. We consider a single antenna base station, and this single antenna is just like a fixed position antenna, like the conventional antenna. There's no MIMO there, okay, remember. So we're doing all these rate splitting from the transmitter side. So we are serving multiple user, okay, multiple user, this mobile user, but all these mobile user utilize a free intense system. So therefore, okay, user 1 like this, all these other users the same. So I have a service which I can switch the position of the reception, okay, and then I have a 2-dimensional space, and I have finite number position I can switch, okay. So this is the only new element, new ingredient that we're introducing to the model. So, okay, so the rest is the same. You're still doing rate splitting, okay, doing decoding of the common message first, and then interference cancellation, and then before you do the decoding for the private message next. So we're doing exactly the same thing like RSMA need to do, okay, but just the difference is that, okay, so, okay, that's my cat, okay, so, okay, apology for my cat is screaming sometimes, okay. So then, okay, so basically you're doing this, okay. So it's a dynamic system, okay, and each user only have one RF chain because we only turn on one particular position and then get this signal in order to do the decoding, okay. So our contribution is we analyze the, we perform this sort of statistical analysis. We look into outage probability because it is easiest to understand, okay, mathematically. So here are the results, okay. So there are a lot of results that we're showing, but I think we can focus on just one. This is easy. But if you would like to ask, okay, how do we control the power, or the power over common message, private message, and all that stuff? We don't optimize it. We didn't optimize it. We just fix them, okay, and see what happens, okay. And then of course we have other results. Try to play around with different parameters and see the sensitivity of the result and all that stuff, okay. But I think the key message I like to share, we can just forget about all these complicated different parameters and then the interplay. Just focus on these results. Let's say this is the signal to noise ratio. Okay, this is the outage probability. Of course, we want outage probability to be small. Okay, this group of results is about when the mobile user is using fixed position antenna. Here, TAS core is about traditional antenna system, like, okay, no free antenna system. This is the error probability, the outage probability, okay, according to signal to noise ratio. Of course, we need signal to noise ratio to be high to make it work, okay. Otherwise, too tough, okay, for the decoding, okay. So, but the good news now is we changed the slope of the outage probability for the user by a lot, right? You see, this slope and this slope. So let's say maybe if we want 10 to the power minus 2 outage probability, then you would need like something like 60 dB. But now we're bringing it down like 40 dB, right? 40 dB, 50 dB. So we're bringing that 10, 20 dB reduction in the signal to noise ratio. That would make RSMA a lot more popular because the more situation that you can utilize RSMA. Otherwise, we may complain that, okay, RSMA you cannot use it now because the signal to noise ratio is not high enough, okay? Or you would need really, really powerful error correction code. But remember all these results, there's no error correction codes, okay? So second situation, okay? Second situation is the same, okay, free intense system, again, RSMA. but then we put a star risk in between. Okay, we feel that okay, this is kind of fun to do. It's kind of tricky because the direct line of sight is blocked this time, and then we need to use risk. But you know, there's nothing more fun to consider star risk than just a normal risk because you have two sides of the user, transmitting user, receiving user. Okay, maybe these form a very interesting pair, which the rate splitting would be effective, right? Because you have two user, we do RSMA, but then we have transmitting and receiving user, right? Again, right here, we're focused on using free antenna system onto the user. The base station is still single antenna, single fixed position antenna, okay? So there's a risk, okay, and then a star risk, okay, then doing optimization. I think right here, okay, the star risk, the operating protocol is energy splitting. So signal comes in and then it will split into two portions. Part of it go to transmitting, part of the energy go to receiving. That's what we talk about. And we only focus on two user right here, okay, in this situation, because just one transmitting user, one receiving user. Again, we are studying we have studied the outage probability. We also look at the average capacity as well. So here come the results, okay? I forgot to put in like the average capacity results, okay? I only focus on the outage probability here. But in fact, in this work, we also consider what we call phase mismatch star risk. And that means, you know, when we need to optimize the star risk or risk, we need to optimize the phase elements, right? The phase response. But then we assume that there's going to be error, okay? Maybe there's some finite resolution of the phase control or some other thing. So therefore, it's not going to be perfect. So therefore, we also incorporate this mismatch into the model and see how that affect the results, okay? Well, the good news is right here, these two lines, again, these two lines is a traditional antenna system, okay? Right? And one with phase error, one without phase error. So with phase error, you can see, okay, so let's say even it's ideal, the star was ideal, the error probability will still be kind of not so good, okay? So if you need to improve it, okay, well, if there are phase error, it's even worse, okay, another order of magnitude degradation. But we've talked about all these group of results, okay, you can see all this line shift, its slopes change completely. The outage probability becomes much more desirable. Why? Because of diversity, okay? That the free antenna system allows the users to change, to improve. So therefore, now we bring down the outage probability so much that would make RSMA would be meaningful in practice. So this is the number of star risk elements. So this is the average signal to noise ratio. Again, we see that this loop bring down a lot. But of course, there's kind of like a threshold that you need to hit beyond this. Before this, probably nothing helps, okay? But of course, you know, you can improve the maybe the size of the front end system, the resolution, then you can probably shift this to be to the left-hand side a little bit. Now, the third situation that recently also we consider is the following. Again, for NSS system combined with RSMA, but also now we include another element. Now there's no rest here, but we have the UAV as the relay. Okay, so we have the UAV doing this decode and forward relay. Okay, half duplex. Okay, so there's two slots. One slot taking the signal from the base station, and then the second slot, the UAV relay the data by re-encoding this data to the users. Okay, so this is what we call the ground user now, ground user. But all these users now equipped with free internet system. Okay, so again, there's an object, okay, blocking the signal, and then we need the relay to help out. Okay, so again, you know, Fasha, okay, the first author of all these work, he is a mathematician. He's really, really strong. So he likes to do a lot of performance analysis. So again, you know, he was using, you know, a coupler theory to analyze these very, very complicated channel scenarios, and then to try to understand what is the outage probability of this system, and then okay, yeah, and then the asymptotic analysis just try to understand the diversity analysis as well. So therefore, it's doing this. Okay, so what happens? Okay, there are a lot of results that I don't think that, you know, I like to go for all of this. So for example, these results I remember. I know. I will finish later on. So okay, so these one because it's requested by the reviewer, okay, they want to see the difference between NOMA and RSMA, so we produce it. So, but I think what I would care most would be these two results. But maybe let's just focus on these results because this one is more clear, okay? So it's about, again, these two lines, okay? The ground user 1 and 2 using traditional antenna system, the fixed and precision antenna. But then the other ones, again, using full antenna system, that we are able to drive, okay? The result, the output probability to be so much smaller, okay, with huge diversity, so that we bring the diversity order down so much that make RSMA effective in practice, okay? So I think I'm spot on. Okay, so this is the time. Okay, 15 minutes. So this is conclusion. In fact, my conclusion is simple. Okay, also of course, first of all, here I show a lot of places that you can access more information. If you're interested in foreign system, you can go and take a look. And then there are some information that hopefully that we would update it daily. More video on the YouTube channel. More useful more recommended best readings that you can pick up, and then other resources as well. And then we also plan to upload codes. And then if you try to get some codes that related to some of the published work, you can feel free to contact us as well. We will try to be helpful to you. Now, but at the same time, so what I want to highlight here is this. Okay, what I like to highlight here is this. Rate splitting multiple access is an emerging technology now. Is becoming a key technology. I like RSMA. I also like NOMA. Okay, but of course I like RSMA probably slightly more than NOMA because of the rate splitting architecture, which eliminate the need of user ordering. So I think that maybe give me a little bit edge of RSMA in this sense. Okay, but at the same time, I do understand that when it comes to successful insurance cancellation, we cannot ignore, okay, these practical challenge, because in the end, no matter how nice on academic papers that we see that there's so much race gain, but it's a different story when we try to look into in practice what happens, because then the channel conditions play a role. Sometimes we need to impose a lot of channel coding. This may not be the right thing to do because then it compensates your capacity gain. So I hope today what I cover actually give you another perspective and say, okay, hang on a second, maybe successful interference cancelling is not that terrible if we have technology like for instance system like this that that could sort of compensate the need of doing error correction code. But I have to say, I'm not suggesting that we don't do error correction code. I'm not saying that. I'm just saying that maybe we can have another technology to go with it so that we don't need as big a block length that we used to have, or maybe we can sort of relax the coding rate a little bit so that we don't code so many redundancy. So because we have some help, from somebody, some other technology like for instance system, then in the end, maybe this would become a good combination that make RSMA even more attractive. So for this, okay, I conclude my talk, and then I hope that you enjoy my presentation. I'm happy to answer some questions. So over to you, 1J.
Yeah, thank you for your very inspiring talk. So I think we have some questions from the audience. So so maybe also you can check in the chat box.
Okay,
So
yeah, I'm opening up the chat box now. Okay, let me take a look.
yeah, so then maybe I can
Okay.
read it
Yeah.
from
So the
Berlin.
first one, okay, so nothing. All right.
Challenge.
Zulin, okay, so I hope that I pronounce your name not too wrongly. Okay, besides the problem existing RSMA, what new challenge will be brought while combining RSMA and front end system? Okay, maybe I thought that you're talking about front end system, right? Because you mistyped this. Okay. There are always challenges because there are academic challenge and practical challenge. Okay, these are two different type of challenge. Okay, both are important. Of course, academic challenge, there are a lot, okay? Because when it comes to even RSMA, I think academic challenge, when not this is not limited to RSMA and FAS, okay? Finite block length, what is the race? Okay, in theory, this of course itself is already very difficult. Now, and also in practice, remember one thing that I actually like to bring to the attention to the community is that most people, including myself, focusing on structural efficiency, capacity. So these quantity is good, okay, very, very powerful. But sometimes we need to step back a little bit because those metrics assume zero error probability, okay? This is good in terms of focusing on, okay, the rates, okay? So this because it's the fundamental limit that would give us the indication of the achievable performance. But at the end of the day, okay, if now I tell you another situation, what if we need to share the spectrum over 10 user, okay, not too many 10 user, okay? But in fact, I don't need to concern about zero error probability. I'm okay to accept that all these 10 users suffer some error probability. Let's say 10 to the power minus 5, because I think 10 to the power 5 would be good enough for my, let's say, IoT application or whatever. 10 to the power minus 5, this is all I ask. Then if you look at the channel, theoretically, let's say some analysis, some mathematician did it and say, oh, the degree of freedom, okay, of the channel is 5, let's say. Then the conclusion is that we don't support 10 user. No way. Because the degree of freedom of the channel is just 5, okay? No way you would try to push it to 10 user. They would stop it. They would eliminate this need. You don't do it, okay? But in fact, it doesn't mean that in practice, some people would be giving you a technology where they can actually support 10 user with 10 to the power minus 5 minus 6 error probability. This is still possible. These results does not contradict with the fundamental limit of Shannon. Now, then there's the difference here. That means, so if we talk about massive connectivity, should we just talk about degree of freedom? Maybe not, because degree of freedom is misleading somehow, okay? Because they need to focus on two perfect situations where you can actually decompose the channel into independent streams, okay? Not all the time you can do it, but it doesn't mean that these will limit the number of users that you can support. So then, even massive access, you have this situation, you have this crazy difficulty. So therefore, RSMA is the same thing. So I think to be useful for the next stage, okay, regardless of how fundamental of the results that we have available so far from in the RSMA community, there's still a lot to be done. For example, what if we don't rely simply on link level simulation to work out what you get? But then how about, is it possible to come up with something? Let's say I just randomly throw it to the table right here. Do we have what we call practical degree of freedom or effective degree of freedom? But then this is related to the kind of error tolerance of the network. Then maybe we would have a different light or different understanding of the achievability of RSMA or fully intelligent system. The reason why I concern this a lot, because I understand fully intelligent system. This is the technology which try to play around with the fading phenomenon and then to our advantage to do our transmission, reception, whatever. But at the same time, we don't want to do too much in terms of the signal processing. Now, if we don't want to do too much of signal processing, for example, using fully intelligent system, now there's a problem. The problem is that if we try to use fully intelligent system to deal with interference, maybe the interference will never be zero. Because it's unlike MIMO. MIMO, when I do zero forcing, the interference is zero, okay? You cannot beat this. Interference is just zero. But if I play around with the fading, I only take advantage of what the fading gives me right now. So the interference may be a lot smaller, but it's not zero. Maybe 0.1 compares to the decided signal 1, whatever. Okay, it's never zero. So, but if you look at degree of freedom, no, you still get 1 degree of freedom because you don't get zero interference. So then I have a strong feeling that there's something missing there. So then when we consider RSMA for the system in massive access situation, there's something which is not ready. The theoretic analysis right now is not ready, okay? The classical Shannon theory is not ready, okay, to look into this. So therefore, these will be the academic fundamental challenge. In practice, of course, the practical challenge will be something else. The practical challenge will be like, we can do all this enabling technology. Should we do all of them together at the same time? Well, maybe not, because it's too complicated, right? Each one maybe bringing something new to the table, so you need to trade off, right? I think RSMA is the same thing. You can do multi-layer RSMA, then why you stay at one layer? Well, maybe if one layer do the job, you will stop at one layer. If not, you will do two layer. Or maybe if needed, you do three layer. But at some point, you will stop based on the feedback from the challenge in practice. So therefore, then you have two choices. One choice is that, okay, how about we do two-layer RSMA? How does that compare to one-layer RSMA, but with full intent system, let's say, right? I mean, we don't know, right? We don't know. Maybe we can simply do two-layer RSMA and then it does the job, and then I don't need full intent system. Maybe that's the case. So it would be a lot more to look at to have a fair comparison and to really understand what's going on. I think risk technology is the same thing. Over the past 10 years, well, not past 10 years, past 5 years, okay, there's so much interest in risk. But the more we work on it, the more we realize that we're not ready. I think that's that. I think probably is one thing that we learn. Okay, I hope I answered your question. Now let's move on to another question. Yu Yang Liu, okay, thanks for the question. In the FAS RSMA example 1, full antenna array includes a large number of active ports. My question is, what do these active ports play and how do they benefit the RSMA system, specifically how they help reduce interference at the receiver side? For instance, does the receiver dynamic adjust the active ports control the beamwidth directivity? Okay, all right, okay. So thanks for your question. So now let me just just go back to let's say, okay, is this right? I know we're talking about this example, but I like to just show this. Okay, let's say this one, or maybe this one. This is easier to explain. Okay, let's imagine this is actually the full antenna system that we imagine. There are a lot of position, and a lot of this position is like some sort of electronic structures, slot structure. In fact, if you take a closer look at it, this is like a what we call the dual slot structure. So all these elements somehow play a role in creating the directivity or radiation pattern that you focus on the antenna characteristics. Okay, it will create something. It depends on how you tune or how you which part of the electronic structures that we activated. Okay. All these radiation pattern directivity would change slightly, but in this design, I remember if I spoke to them, the main thing is that what mainly change in this design is that the antenna aperture change. For example, if I activate this and deactivate the other, basically it's more like the antenna radiation pattern, just appear right there. Okay. But if I activate this part and then deactivate the other, the radiation pattern appear right there. Okay. So what does it mean? It means that we are achieving antenna aperture reconfigurability that take advantage of spatial diversity that is being observed from MIMO antenna system like many years ago. Okay, but what we do here is that we just achieve this, but not doing multiple antenna, but a single antenna structure with a shared aperture that they can be reconfigured. Okay, so now then if you do this, then how interference is going to be smaller, right? Okay, that's your main question. Now you do this, how the interference is going to be smaller. I forgot to put this slide right there. Okay, so this is the following. Okay, how much interference that you get, it actually depends on the exact location of where you receive the signal. Okay, on the antenna. We see this, we experiment this, we demonstrate this, not just me, but around the world from MIMO antenna system. People know that when they put multiple antenna instead of one, okay, if they are far apart or whatever, okay, then they receive different signal magnitude. Let's say the interference, okay. So some position, the interference will be stronger than the other. So therefore, when we are now saying that we have antenna that can switch the position, you can actually take advantage of this variation in space against interference. So that's why when you switch the position, you could activate the portion of the space where you can observe the interference, but with weaker magnitude of the interference. This is how you avoid interference in this sense. Okay, maybe you have a follow-up. Okay, let me look at this. I hope that I answered this question. Okay, you got it. Thank you very much. Any other question?
Any other questions? Maybe I have one. So I haven't
Yes, please.
actually know that you have a lot of like a work on combining the RSMA and the FAS.
Yes.
And I was wondering, sorry, I think oh, okay. So I think in this, I think the three of work are in commonly they assume that there is only the single RF chain at the transmitter side. But
Yes.
as far as I know that for the like a single like a broadcast channel cases, like a it's not a multi-user MISO. This is just for broadcast channel, right? If the transmitter has only the single antenna. In this cases, I think the normal RSMA does not have a lot of the benefit compared to the normal. So in that cases, what do you think about?
First of all, okay, so we did have other works consider using for instance system on a normal system. Okay, I can see that, you know, I know where you're coming from. It's like, okay, in this situation, in fact, it's not an ideal situation to consider RSMA. You know, in RSMA situation, maybe we would like to consider, let's say, having multiple antennas at the base station, right? Just to start with. We also like to consider multiple antenna at the base station to start with. The reason why we didn't yet, okay, we haven't done it yet, because you can see the contribution in all these three works, we focus on the performance analysis. When there are multiple antennas at the base station, wow, this is so hard, okay? Because we need also concern about the precoding structure as well. These probably would be responding to the instantaneous CSI. So then this would probably eliminate any possibility of looking into the analytical result that we try to achieve. So because of this limitation, we then back off and say, okay, maybe we consider a single fixed precision antenna system at the base station now. And the objective, for example, our objective was like, if we can show, even in this really difficult to handle situation, because we don't have multiple antenna at the base station, then we can see grid system can bring so much to the scene. Well, then maybe it would encourage people to say, okay, now this is the time that maybe when we consider RSMA system, we could consider for instance system at the user, or maybe even at the base station side, or maybe anywhere, and then to see, you know, the synergy. Okay, so therefore we are limited by what we have been able to do so far. So that's the only reason why. In fact, okay, I actually like to think that, okay, typically you should have multiple antenna at the base station. I mean, this is what the base station will make for, right? The 5G, they have 6-foot antenna. 6G, maybe people talk about smaller base station with 32 antenna, whatever. There's always going to be multiple antenna, and then doing pre-coding as well. So therefore, to me, the next stage, hopefully we'll try to get to deal with it, is what if we also consider free antenna system to be integrated with the multiple antenna at the base station, or maybe, okay, together with free antenna system at the user, or just free antenna system and the user side. But then, you know, of course, we're struggling, you know, what we should focus in terms of mathematical analysis. What can we do? Okay. And I remember, okay, one of the work I collaborated with South University in Warwick University, we actually considering a cell-free MIMO. Cell-free MIMO system in the network using stochastic geometry. And then we also consider free antenna system as a user. That can be done, okay, but because then we have to use, you know, random process and all this stuff. But then those situations we couldn't consider RSMA, okay, because it's so hard, right? But maybe it's time to look at this again and say, okay, we need to do something in between, right? So I agree with you, but we have our own reasons.
Yeah. Okay. So I think, yeah, because of so RSMA has a lot of like a kind of the sensitivity for the, I mean, sensitivity of the SIC error, SIC like a error propagation or something like that. So FAS can reconfigure like a so that maybe they can help to improve the
And
weakness.
also one thing, I don't know, if we look at this result, people can have different interpretation. But I would like to challenge the community and say, okay, yes, we do see that in the future or now we have multiple antenna at the base station and then doing all this stuff, okay, pre-coding, all that stuff. This is still valid.
Yeah.
But what we missed is, what if we are not talking about cellular structure? What if we talk about device to device, massive IoT situation? Then a lot of people will be saying that, okay, in this mass IoT situation, we probably wouldn't be able to do RSMA, we wouldn't be able to do pre-coding, we wouldn't do normal, because come on, it doesn't really well. You can see from the result. If you don't do this, okay, there will be a lot of successive interference cancellation error. That would be like not a good situation to use RSMA. But maybe this is not entirely true. Judging from this result, I could even say that maybe we could have a massive device-to-device connectivity situation, right? There would be mini broadcast channel like here and there, so one to many, IoT devices, but then all these base stations are distributed, okay? Then how do we manage interference across the mini base station if they are uncoordinated because they are not doing beamforming together? Then maybe you can do scheduling, okay, maybe you can do frequency allocations, things like that. But at least on top of that, we don't need to worry, or we don't need to impose a requirement of having a large array of a transmitter to talk to multiple receiver. These open up a possibility where you don't do anything, okay, from the transmitter side, but you can still talk to multiple IoT devices using RSMA. How nice is this, right? This is a opportunity where probably even the RSMA community would be like overlooking this because, okay, we want to make sure that we're pre-coding so that this work well and all that stuff. But then forget about the potential that this could be actually applied even to the situation where pre-coding does not exist.
Yeah, I think, you already show a lot of the synergistic gain of the RSMA and FAS antenna system. So yeah, I should definitely follow all your paper.
Okay, thank you very much. Thank you very much. I see someone raised a hand earlier. I don't know, but I don't know whether it's still there. The hand is still there. Oh, yeah. Sajay. Okay, yeah.
Yeah. Thank you. Thanks a lot for pioneering talk, Professor. I have a question about how many ports of the antenna should be active in fluid antenna system.
Okay. This is very general question. How many ports you should activate it depending on the receiver architecture? Because even I myself, I propose a couple of receiver architectures. Some activate many, some activate one, okay? And of course, there's another discussion or another consideration you can consider is like, normally if you have, let's say the receiver, you have multiple RF chains, okay? Let's say if you have 2 RF chains, 3 RF chains, you would expect that at least you activate the number of ports according to the number of RF chains so that you can activate multiple and then you do signal combining, right? So, but even you only have 1 RF chain, even you have only 1, it is possible to activate multiple ports to mix the signal to improve the interference cancellation ability. This is, there are a couple of papers that I proposed, I call CUMA, okay? Try to search it up because I forgot to put it in my talk. Then you will see that this is possible to activate multiple position, then mix the signal in the analog domain to improve the interference reduction capability, even though you only have 1 RF chain or 2 RF chain. But the most simple version is what I talked today. Just activate 1 position, get 1 signal out, and then deal with it, okay? So this is the easiest, the simplest version. But there are more advanced versions that could do better, okay?
Thank you, Professor. I'm sorry, based on which strategy you should be active more than 1 ports?
Okay. Okay, I'll type it in the chat, okay? So CUMA, there a technology called COMA. Okay, give me a second. Let me just copy the paper, at least the information about the paper that you can try to. Okay, just a second, because I'm trying to find this paper.
It's a compact ultra-massive antenna.
Yeah. That one. Exactly. Okay, it should be very quick. Okay. Compact.
Just share in the chat box.
Oh, okay, I find it now. Because there are multiple windows in my machine. It's a little complicated to control. Oh yeah, you have it already. Okay, so
yeah.
So this is the technique I was talking about, that I should say it is possible to activate more than one port, maybe many. Okay, out of, let's say if you have 400 position, maybe you would choose to activate 50 position. Then you try to do analog signal processing and then some digital signal processing to improve the interference rejection capability. This is possible. So in fact, this is a good point. In fact, I could change the results that I reported today with RSMA by saying I'm using this technique. I can use this technique, okay? And then, well, the outage probability will be even less. Yeah.
Yeah. So
thank you. Thanks a lot, Professor. Can I ask another question?
Yeah. Go ahead.
I'm sorry.
No,
is that
no need to
possible?
sorry. I should thank you.
Thanks. Professor, is that possible to use FAC in the transmitter?
SIC in transmitter, right?
FAC, fluid antenna
Oh, yes.
system.
FAS. Yeah, FAS. Yeah, FAS, right? FAS,
Yeah.
fluid antenna system. Yes, obviously. Because there are papers that actually we publish focus on integrating precoding with fluid antenna system at the base station side to do, for example, ISAC. Okay, we have some papers on doing that, for ISAC as well. Okay, using mixing fluid antenna system with precoding at the base station. We can even do both sides. Fluid antenna system and user side, fluid antenna system and precoding at the base station. Do this. And there are other versions that we're using the position flexibility concept and then integrated on wrist. We have done that. Okay, so we have a large number of elements on wrist, but then each element can change the position within a certain area. We do it for star wrist and wrist as well. So there are so many possibilities. But at the end of the day, each model needs to be judged independently whether this is a legitimate or valid model, because we can always mix and match different stuff. But at the end of the day, we would need, we will have the duty or responsibility to explain why we put these things together. Okay, what's the reason? Right? It's not just mixing A plus B plus C plus D, right? We need to have a proper justification. For example, I hope what I have done today is I make RSMA and the fluid antenna system not because just A plus B, but because I see an opportunity or an issue of RSMA that need to be addressed. And I see fluid antenna system could be a nice solution to address this without causing troubles, okay? So then it could take RSMA to a next level. So then, these probably validate, the idea, rather than, I just simply do fluid antenna system plus physical security plus wireless power transfer plus caching plus AI plus ISAC, plus UAV plus Taurus, right? I can do this, but at the end of the day, we need to be more sensible. We don't just mix. We mix them with a logical thinking, with rationale behind it. We need to know why.
Thank you. Thanks a lot, Professor. Thank you.
Thank you. Thank you for your question.
We have enough Q&A session. So
thank you.
Thank you, Kid. So I think we have to wrap up here. So thank you for your very inspiring talk and Q&A, empathetic Q&A session. So
Thanks.
I hope, yeah, all of you enjoy. Yeah, I think I'm sure that, yeah, everyone here enjoy your talk and learn a lot of the synergetic gain between the FAS and RSMA, right? Thank
Okay,
you.
so just my final sentence. Okay,
Yeah, sure.
thanks for attending my webinar, and then I love the opportunity, and really thanks for the interaction and audience question. I hope you like it. But again, in December, I'll see you one day. Okay, I'm traveling to Korea.
Yeah, sure. Definitely you have to contact me.
Okay,
And
bye bye now.
go to Bulgogi. Thank you.
Bye.
Bye
Bye now.
bye.